Alright, so welcome to the video lecture series of digital electronics, and today we are going to discuss about our module 4, in which we will discuss the registers and counters. So we will start our discussion with the registers, and the register in digital domain is come with a special property, and those special properties are like you have to store the data in the registers, or you can shift the content of the stored data which you can store in the registers. Okay? So first, let me formally introduce what is registers. So when we say registers, then registers are nothing but a special group of flip-flop. Okay? Register is a group of flip-flop, and a group of n flip-flop is known as n-bit registers. For example, if somebody says we are having a 8-bit register, then it will be able to store a 8-bit of information in it, right? So this thing you should have to always care that how many number of bit is there, then it is something directly which is related to number of flip-flop used in that specific register. Thirdly, the registers are essentially a synchronous system. This is very important point, because as we know, these are a group of flip-flop we are using to construct a register. So all the flip-flops which are connecting either in a cascade form or in another form, they will be operated by a common clock pulse. That's why we will call these registers as a synchronous system. The feeding of data in the register is known as loading and updating the registers. Again, this is the important thing which you should have to know. Means if you want to store the data, then you can also say that similar name, load the data in the register. The loading or updating the data in the registers can be done in two different forms. One is serial loading, another is in parallel loading. Very importantly, you should have to also note at this point of time that the serial data is also known as the temporal code, and the parallel data is also known as the spatial. We will discuss about these codes soon after this slide. Next, let's classify our register, means how we can classify our register. So there are a lot of ways to classify the registers, but we classify the register on the basis of three important points, in which the first is based on the application. Okay. So based on application, register can be classified as either the storage register or the shift register. Okay. Storage register, as its name suggests, you can store some content or binary information in it, depending upon how many number of bit register is given to you. For example, a 4-bit register can store a 4-bit of information. 8-bit register can store 8-bit of information. Next is based on application is shift register, and in shift register it can shift the data from one flip-flop to its adjacent flip-flop. So one by one, an incremental shift can be done with the help of this register, and which makes a very useful application in different domains of these registers. Okay. So while you are connecting the flip-flop in cascade and shifting the data one by one, then of course the output of one flip-flop is connected to the input to the adjacent flip-flop. So this kind of a series connection is there, by which you can connect your flip-flop to form a register. Okay. Second classification is based on the mode of input and outputs, and in our syllabus we will discuss a little bit detail about this mode of register classification based on the input and output. So the first is the CISO stands for serial in and serial out register. Of course, the data which is going to be input in this kind of register will come in the serial fashion, and the output which has been extracted from this kind of register will of course come one by one in a serial fashion also. Second is the serial in parallel out register. Data input will be done in serial fashion, but you can read the data on parallel. Parallelly you can read the data. That's why the SIPO, serial in parallel registers are there. The third category is the PIS, which is parallel in and serial out register. By parallel in and serial out register, the data will be parallelly uploaded in the registers through their input, which directly connected to the all flip-flops, concerned flip-flops, and but the last flip-flop will give the output in a serial fashion. And the fourth category is the PIPO, in which the data will be loaded in parallel fashion, and the stored data will be read out in the parallel fashion. So that's why this is known as the parallel in and parallel out registers. The third classification is based on the direction of operations, means how it is actually loading the data either from right side or from the left side. So based on that, you can classify your register in different category, in which one category is the unidirectional, means the data will be shifted from left side, or data could be shifted from right side. So this is the unidirectional a property of the shift registers, and by which we can classify our register left shift register or the right shift register. And the next category is bidirectional, means with that you can have a control over, through the use of that control you can shift the data in both directions, like either in right direction or in left direction. We will discuss in the next slide. The next important thing regarding the register is that the clock pulse required for the proper operation of these registers. So if, for example, we are considering a n-bit register here, then there are two different cases, means for serial data input and parallel data input we can able to get the exact number of clocks required to produce the output. Okay, for example, if we are talking about the serial data input, then to input the n-bit data we required n clock pulse, and to output the n-bit data we required n plus 1 clock pulse. Similarly, or in other side, the parallel data, for parallel data to input the n bit of information we required 1 clock pulse, but do not require any clock pulse to read the data. Okay? So that's why we have written over here that the output of n bit is required 0 clock pulses. Now let's try to understand the first serial in serial out register, and especially we are discussing the 4-bit right shift register in this slide, and you can see that the whatever we have told you earlier in the earlier slide, that the registers are nothing but a series connections of the different flip-flops. So you can see we are using 4 D flip-flops here. These are the 4 D flip-flops, and a common clock pulse is applied to all the flip-flop, because we have already told you that these registers are synchronous system. That's why we can provide a common clock pulse to all the flip-flops. And at this point, you can also see that the output of the first flip-flop is connected to the input to the adjacent flip-flop, like this. You can see that these dot points moving, and serial input is applied to the first flip-flop, which you can say the MSP position in the data, okay, or in the data which is given to you. So the first flip-flop will represent the MSP once the all serial data will get in this 4-bit right shift register, and the last flip-flop will be called as the LSP position of the flip-flop. And this small clock pulse diagram is represented over here to give you an idea that there might be a regular uh, uh, rectangular clock pulse or a square clock pulse to be used to operate the overall shifting of the data in this serial register. So to understand the operation of this 4-bit right shift register, we draw this table over here, and in which the first column represents the clock, in which and the second we represent the data which we want to serially in this 4-bit right shift register, and the next columns are actually representing the output of different flip-flops. See, for example, the MSP flip-flop output is represented by Q3, followed by the Q2, Q1, and Q0, which represent the MSP. Okay. So now, when there is no clock pulse, this is the in absence of clock. If you apply the data, serial data input to these at this first terminal, at the T terminal of the first flip flop, then what happens? It do not the circuit will not get operational. So you can see we mentioned here all zeros initially. Okay, output all outputs are initially zero. But when the first clock pulse comes into the picture, then the first bit will start moving, and the first bit means you can say in this data, this is the first bit which will move first and enter in this system. So the output Q3 will get updated with this data, and the remaining output will be shipped by one bit position, just because a common clock will operate all the so similarly, when the second pulse is come in, then the second data will be input to the first flip flop, and there will be a shift in the next flip flop output. We can observe with the help of these yellow arrows. Similarly, for the third and fourth clock, this all the four data will be get in by following this first flip flop register, and this will shift. For every clock, there will be a shift of this data to their adjacent flip flop, and they will update the output of their flip flop. Okay. So finally, after fourth clock pulse, what you will observe that your all data means 1010. If it is your serial data which you want to enter in this flip flop, then after fourth clock pulse, your all data will be getting. And of course, just I told you that this Q3 represents the MSP part, and this Q0 represent the LSP part. So you can see the 4-bit data is already there. Now what happened when the fifth clock pulse comes in? Then this first 0 will be taken out from this 4-bit write shift register. So in this way, actually, our serial in serial out register works. Okay, so data will be input serially, and we will take data out serially. That's why it's named serial in serial out register. And of course, if you observe the flow of data, then your flow of data is from right to shift, left to right. That's why we are saying this is the 4-bit. This is the 4-bit right shift register. This is the 4-bit right shift register. If you change the direction of data flow, in that case, what happened? The data initially which you put LSP part first in through this input terminal. If you put the MSP part first, then the direction of data will get changed. So you can observe here that in this diagram we are talking about the 4-bit left shift register, in which here you can see the data serial data is input from the left direction, and the fundamental difference is that in right shift register, this LSP parts goes in this register first, but in 4-bit left shift register, the MSP part will be input first, and then it will, as per the clock, as the clocks number of clocks increasing, the data will be shift from left to left, left direction. So we will call it as a 4-bit left shift register. Okay. So now let's talk about the another category of registers, which are these SIPO, serial in and parallel out register, in which we can see that the data will be input just in we talked in the serial in serial out register, but what happened? The output you can observe, or output you can read at the same time, or when the all data will get input, means, after 4th clock pulse, you can directly read your data. You do not require additional 4 clock pulse to finally serial out your input information from that register. Okay. So the data will be serially in. It's with respect to every clock pulse, your data will be input based on the LSP part goes in first, and then the other higher MSP bits of the data will be get input as by following the clock pulse. And you can observe here that we take the output of every clock pulse. Okay. So once after 4th clock pulse, when your all data will be getting, you can directly read the data from these terminals Q3, Q2, Q1, and Q naught. Okay, so that's why this data, this kind of arrangement of the flip flop, which construct shift serial data in and parallel data out. Okay. So you have to remember one important tagline about this C4 register is data will be input serially, but the data once the data will get input, then once the data get updated, once the data get feed in the system, you can just after that you can read your data. Okay. Now, this is the case where we are actually input the data in a parallel fashion and read the data in serial fashion. So, to make this arrangement, again we take four D flip flops here. These are the four D flip flops. We take and we provide a one common clock pulse to all the D flip flop. This is a common clock pulse. And input we entertain in such a manner so that if through one control input, once this control is operated, then with 0 and 1, we can at one control we input the data and another control input is applied, then the data will be get serially out. Okay, so how to do that by making this control enable for parallel data in and serial data out, we actually use the mux over here, and in that mux actually the select input is connected to the control. Okay? Select input is connected to the control. Now see what happened when you provide the control 0. Okay, when you provide the control 0, then of course the property of mux says that for 0 select input, the first input line, this first input line will get enabled and it will translate at the out. Okay, so what happened when the control is 0? So when control is 0, then this D3 and D2 information and D1 information and D0 information will directly apply to the individual flip-flop. It means you can see the connection. You just follow the red dot here. Means once your control is 0, then what happened? This is the input data flow. Okay, this is the input data in which the data is getting input parallelly, and when the control is 1, then what happened to your second data, means this information, this line is getting enabled because this channel will be transferred at this output of the mux. So this channel will get enabled, and now this follow this propagation of your data. So that's why once the clock control is 0, that parallel data get in, and when the control is 1, whatever the parallel data you have stored in this system will be serially out in this fashion. Okay, that's why we nomenclate this kind of arrangement of the flip flop to construct the register is parallel data input and serial data output register, or PISO, parallel data in serial data out. Now, the last but not the least, you can say you can make a lot of universal register kind of thing, or many more register you can construct, but these are the individual classification in which we are talking about the parallel and parallel out register, in which data will be parallelly in and you can read the output parallel. Okay? So you can observe here that again we use the 4 D flip flop here, which are connected to a common clock pulse to follow the synchronous design, the synchronous system design constraint, and data will be input to the individual flip flop through their input terminals, and their output terminals you can extract the output at the same time. So what happened? And interestingly, only one clock pulse is required in this arrangement to input the data, and no clock pulse is required to read the data, because see, when the first clock pulse comes in, immediately all the data which is applied over here through the D3, D2, D1 and D0, they will get updated they can change the output of their respective flip flop at the same time. That's why we are saying once clock is applied, the data will get in, and no other clock pulse is required to the data. So you can see the green lines over here. We represent the parallel data input, and the white lines are actually parallel data output. Okay. So, important conclusion regarding this classification, and especially in case of this PIPO register, is it is the fastest register among all, which we have discussed in the previous slide, and it cannot act as a shift register. See, because you can definitely you can observe that there is no connection of the input output in between these flip flops, so there is no shifting kind of thing happening. So the data flow is not there, so you cannot use this PIPO register for shifting purpose. And this is very important thing which you should have to always remember, that only the one class in this category of shift register cannot be used for shifting of the data. But yes, of course, this data can be used. This data can be used as a storage register. You can store the information. Now, let's try to understand one example of the shift register and how they get updated their content. Some external logic has been applied to the output of these flip-flops. So there is one data is already given to you in a 4-bit register, and you are supposed to ask what happened when the 4th clock or 5th clock or 6th clock was. For example, in this example, actually, initially content of a register 4-bit serial in parallel out register, because you can see this data will be get serially data is serially uploaded in this register. Okay, and then what happened, you can directly take the output from here, but what happened actually, the last two output are taken and they pass through an XOR gate, and then this data will be serially fed again in the system. So this is an example of serial in parallel out register. And what he's saying that the content is already updated with 0110, and he's asking that what happened when the third clock pulse applied to this arrangement, and what will be the updated content which can be stored in this register. Okay. So initially what we can assume that we make one column as clock, and another is the output of respective flip-flops, means Q2, Q3, Q2, Q1, and Q0. And in absence of clock, of course, there is data is already in this flip-flop. So we just mentioned over here that the data which has been uploaded, given me with the uploaded information, which is 0, 1, 1, 0. And when the first clock pulse comes in, then what happened? The data will be shifted by one position. And when the data will be shifted by one position, at the same time, what happened? This the input of this XOR gate is also getting changed, and based on that shifting and input change of this uh, gate, what this output will also change, and that information will update the first Q3 content. Okay, for example, here what you can see that initially what happened when the first clock pulse comes in, then you can see this content initially is 10, and if this is to the input of XOR gate. So as we know, the when the different input is applied to the XOR gate, output is 1. So this information with this information in the first clock pulse, this get updated to the information 1, and remaining all data is shifted by one position. Okay. Similarly, this one information which has been updated is present over the here. Okay, input 1 0, output 1, and this output 1 will shift. This 0 will shift right position, and this will be updated with 1. Similarly, for the second clock pulse and third clock pulse, this will shift at the same time. This input also getting changed, and the content of the first flip flop output is changed accordingly, and then we will shift the updated information to the side. And finally, after the third clock pulse, you will have this information 1 0 1 0. Okay. So this is an example of 4-bit serial in parallel out register. This is a very important. Okay, so thank you very much, and we will continue our discussion with the next topic, which is counter the next. Thank you so much.